Swayam Prabha. Digital India. Educated India.
Hello and welcome back to the final lecture of this course on control systems. So over the course of the last lecture we have seen with an example of how to design this state feedback controller for a plant which would otherwise not even be stabilizable using this proportional or proportional derivative control action, right. So we have seen that at least in principle if we are allowed to tap into the states of the system and use state feedback, linear state feedback, we should be able to stabilize this. Not just that, we will be able to place the poles in closed loop of the system to any location of the complex plane that we desire. Now we are going to see that same system, but now we are going to design an observer. The principle again being, as we have described so often earlier, that well, if you are not allowed to tap into the system's states, if all that you have access to are the input and the output terminals of the system, we should still be able to design that control action and be able to use some state feedback, right. So provided the system is observable, we will always be able to design this observer, right. The proof of that we haven't really shown you, but it proceeds along the exact same lines as the proof for controllability. Only thing, instead of A you start with A transpose, yeah, and then you have A plus BK, and in case of observability you have A transpose plus C transpose L transpose. So L transpose takes the role of K, yeah, and it proceeds along exactly the same direction. So if A transpose, A is essentially if a system's A transpose C transpose is controllable, it just means that AC is observable, right. So that is all that we cared about for this design of this observer. So just like for AB controllable, we can always design a state feedback to place the poles anywhere. Similarly for AC observable, we can place the observer poles anywhere we like. So again, for that same system, you recall what our system was. This was the system, yeah. So here what we are going to do is we are going to take the same system. Now notice that the way we have realized this system here, yeah, is in the phase variable canonical form, which is always guaranteed to be controllable, but it makes no such guarantees for observability, right. But of course we know that this comes from a minimal realization because there is no pole zero cancellation of the transfer function. So we can also check. So the first thing we check is nonetheless that OAC, yeah, OAC, and I see that C is 0 1 0, and then when I take C times A, so when I take C times A, so 0 1 0 times A, I basically get 0 0 1. So I get 0 0 1, yeah, because this row vector, if you see it, just when you pre-multiply any matrix by this row vector, this is like a selection vector, it just selects the second row of the matrix, right, yeah. So now when we are doing this again, this operation CA squared, yeah, when we are doing the CA squared, remember CA squared, that is going to be nothing but CA times A. So what is CA? CA is this. So what does this vector do? This vector picks out the last row of the A matrix, yeah. So the CA, when operating on A, picks out the last row of the A matrix. What is the last row of the A matrix? That is just this. So it is kind of like a little accidental, yeah, or rather incidental, that in this case, because of the way in which we have cooked up this C matrix, yeah, we eventually get back the observability matrix to be the same as the A matrix, yeah. So the observability matrix turns out to be 20 minus 11 minus 8, yeah, minus 11 minus 8. Please do not be fooled into thinking that in the controller canonical form or in the phase variable canonical form, the observability matrix almost always without exception turns out to be like this. No, it does not. Yeah, this is not in general true, okay. It just so happens that here the way the C matrix has been obtained, yeah, the structure of the C matrix dictates, yeah, the structure of the C matrix itself dictates that, for example, if you had just 0 0 1 as the C matrix, right, then of course the first row itself wouldn't have been equal to A matrix, right, and there is no reason to suppose that it is in general equal to A. This is just incidental, okay, that is what I am trying to say. So in general, do not be misled into the false assumption that the observability matrix obtained from the phase variable canonical form will always be equal to the A matrix. It is not true, it is quite simply not true, it is just true in this particular example in a funny sort of way. And you can clearly now understand that what is the rank of this matrix. Of course it is full rank, right, the rows are linearly independent, so therefore O inverse exists. And what I am now going to do is, because this O inverse exists, I can again, like I did for the controller canonical form, you remember for the observer canonical form, for the observability matrix we have this property, no, that in realization 1 if you have O1A, O1 inverse is equal to O2, A2, O2 inverse, right. So let us say I realize something in the observer canonical form, so let the second realization be in the observer canonical form, yeah, this observer canonical form, then I can write any matrix, the observer canonical form realization as OO inverse O1 times A1 times O1 inverse times OO, right, and I can call this as my T matrix, yeah. So then I have AO is equal to T inverse A1 T, yeah. So again, like I did for the controller case, I'm probably just sort of going off on a longer route to prove the same thing, a very similar thing like we did for the controller canonical form. The same thing holds, you see, what is the typical expression for the observer canonical form? After a bit of practice, from this transfer function, just like I was directly able to write down the controller canonical form, so also I can write the observer canonical form just by inspection. So if you don't believe me, you want to go about it in the long winded fashion. So by the way, let me warn you that I am not going to use any of this. I am just showing you that there is a method that exists, because we did not do it when we were discussing the theory. I thought maybe we should fill you in on that, right. So here is how we do it. You see, from this transfer function, think of the original way in which we obtained the observer canonical form, the first realization we ever saw when discussing state space. So what is this transfer function representative of? This transfer function is representative of this particular differential equation, plus 11y dot minus 20y is equal to u dot. So therefore y is equal to, you have 1 times the integration of 8 times y, okay, I'm missing out the dt's, okay, plus 11 times double integration of y minus, okay, this should be a minus sign here because I'm putting it on the other side, yeah, and then plus 20 times 3 times the integration of y plus, you see, twice the integration of u. So if I now want to realize this through a wiring diagram, as we say, I need maximum 3 integrators. So let me put a bank of 3 integrators here, yeah, and put summers next to them, right. So I put these summers, yeah, and this is my y. I am not putting any feed forward or any summer outside this, because I know that there is no D matrix here, right. So here it goes, yeah. So this is my u, this is my y, and now what do I know? This is my, let us say, x1, this is my x2, and this is my x3, right. So what is this y equal to? Yeah, so this y is equal to minus 8 times the integration of y. So let me go pass this through minus 8 times the integration of y, plus I need to pass this through 11 times or minus 11 times the integration twice. So it better pass through this integration action twice, minus 11 times, yeah, and then plus 20 times thrice integrated y, yeah, and then twice integrated u. So this u, this channel I cannot connect here, right, because this u does not come in here, the u only joins in after this point, yeah. right. So this, of course, I can omit this summer here, does not matter, right, because remember the u gets added only after twice getting integrated. So u has to only pass through 2 integrators, not 3, right. So that is what I do with this. Now with this realization, if I name this as x1, x2, x3, you will see that immediately I get x1 dot is equal to minus 8 x1 plus x2, x2 dot is equal to minus 11 x1 plus x3 plus u, and x3 dot is equal to just 20 times x1. So if I now write this in the canonical form, excuse me as I squeeze out a little bit of space from here, yeah, and of course y is equal to nothing but x1. So of course then the canonical form representation is, I can write x dot is equal to, you see the beautiful thing that happens here, you will see this minus 8 comes in here, minus 11 comes in here, and 20 comes in here, 1 0 0 1 0 0. Isn't this strikingly similar to the phase variable canonical form, right? You see the observer canonical form will always have the coefficients of the characteristic polynomial sitting in the first column in a suitable order, like so. Of course the B matrix has no structure as such, definite structure as such, so this is B, but the C matrix you see is always going to be like this. So just like in the controller canonical form the B matrix used to be 0 0 1, in the observer canonical form the C matrix will always be 1 0 0. So the structure of the A matrix and the C matrix are fixed up in this case, in the observer canonical form. So it is this observation that allows us to see that if you now want to design A plus LC, what happens? You will have this minus alpha 1 minus or minus alpha minus let us say minus a n minus 1 minus a n minus 2 dot 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 till minus a 0, yeah, and then 0 1 0 0 like this, then 0 1 0 0 like this, yeah, and then finally you have 1 here sitting here, and the last row is all zeros other than the first entry. Now this is going to be A plus, now my L1 is L1 L2 dot 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 till Ln times, and the C matrix is 1 0 0 0 0. So what happens? This is my observer's closed loop, no? Closed loop observer is this, and this allows me to read off the observer gains in exactly the same fashion, very straightforward, yeah, it's just going to be minus a n minus 1 plus L1 minus a n minus 2 plus L2 dot 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 till minus a 0 plus Ln, yeah, and then 1 0 0 0 0 like this, 0 1 0 0 0 like this, till you get 1 here and zeros here and 0 here, and finally the last row is all zeros. So this is going to be my matrix, right? And how do I know what these are going to be? Because somebody has told me that I want my observer's poles to be at certain location, so I know the characteristic polynomial of a CL observer. Someone has given me that this should be, let us say, s to the power n plus alpha 1 s to the power n minus 1 plus alpha 2 s to the power n minus 2 plus dot 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 till alpha how many n, yeah, alpha n. So this better be equal to, because in this form you can check that the characteristic polynomial comes out to be nothing but these turn out to be the coefficients, right. So this is going to be s to the power n plus a n minus 1 minus L1 times s to the n minus 1 plus dot 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 till finally you end up with a0 minus Ln. So again you equate each of these terms term by term, yeah. So that is why this observer canonical form lends itself very easily to the design of an observer. So having seen this, yeah, once you have gotten this observer the gains L in this observer canonical form, yeah, now you go back, yeah, now you go back and what will be your gains now? Let us look at the similarity transformation here, right. So you know that your output is going to be the same from both the observer canonical form system and the, so this is let us say the CO times x tilde maybe, this is x tilde is basically this. So in the observer canonical form I have x tilde as my state, in the usual form that I have been given I have x as my states, right. So this is nothing but C0 times T times so then this x tilde and x relation I know this, right. So this is going to be nothing but C0 times T times x, yeah, that is how it is going to be, right. And what is this T matrix? I have already determined what this T matrix is, it is the inverse of the observability matrix in the given form times the inverse times the observability matrix in the observer canonical form, right. So therefore exactly the same fashion, in exactly the same fashion as we obtain a controller parameters from the controller canonical form, there exists a method to obtain the same from the observer canonical form. Two things, one, we are not going to use any of this method, as we have already seen the controller we have designed without converting it to the phase variable canonical form. Now you might say, well, you realized it in the phase variable canonical form, so you did not need to convert, fair enough. In case of the observer, we will show you that even though we will not realize it in the observer canonical form, neither are we going to transform it through a similarity transformation to the observer canonical form, yet by virtue of the fact that the system is observable, we will still be able to design the observer gains in this phase variable canonical form, right. That is what we are going to do, and we are going to show you that by just equating coefficients. So again, for the observer also, suppose, so since this is a toy problem, suppose the observer poles are also desired at -10, -20, -30. You could have chosen anything else also, yeah, this is just my choice, I have just, as a toy example I have cooked this up, right. So now notice that I am not going to do any of this, I am not going to realize it in the observer canonical form again, because it is already realized in the controller canonical form. I cannot realize a different system in a different form altogether, right, then it will be too complicated. I have to realize it in, I have to realize the model in exactly the same form in which the plant is being realized, yeah. So if the plant is realized in the phase variable canonical form, the observer has to be also realized in the phase variable canonical form, right. So this is the phase variable canonical form, this is what I have to work with. So what is my problem then? So again, to reiterate, my system is given by x dot is equal to 0 1 0 0 0 1 20, hang on, let me check what these values were, -11 -8, yeah, 20 -11 -11 -8 x plus 0 0 1 times u, and y is equal to 0 1 0 times x. So this is, again I reiterate, this is not in a suitable form for observer design, in the sense that not in a very convenient form for observer design. This may be very convenient for controller design because it is in phase variable controller, phase variable canonical form, but it is not in the observer canonical form. So one way is, as I have just outlined in the process above, that you can convert it to the observer canonical form through a similarity transformation, design the observer gains by straightforward reading of the coefficients, and then reconvert it back, right. That is one thing you can do, yeah, but I am not going to do any of those, any of such things, okay. What I am going to do is just match coefficients. So what do I need? I need to determine L such that A plus LC has eigenvalues at -10, -20, -30. Again, what guarantees that I would always be able to do this? The fact that the system is observable, although it may not be very apparent and obvious to you here, the proof is exactly the same, that the fact that the system is observable, I can go from the system's realization, any arbitrary realization, to the observer canonical form, and from the observer canonical form I can get a unique gain, observer gain, and then I can again map it back through a unique similarity transformation mapping to get its gains in the representation or the realization that I have got before me, right. So that is all crystal clear, the uniqueness and the fact that I will be able to do this because it is observable. So observability is a necessary and sufficient condition for the design of this observer. Okay, so here is how we proceed. After a lot of talk, 0 1 0 0 0 1 20 minus 11 minus 8 plus here is the gains, the undetermined gains times C 0 1 0. Yeah. So I want that, hang on, again I am making the same type of mistake. So I want lambda I minus this determinant, yeah, I want this determinant to be equal to, or let me not use lambda, let me use S for the variable. What do I want this determinant to be? I want this determinant to be equal to S cubed plus 60S squared plus 1100S plus 6000. Why? Because these are exactly what the poles would be for this, right? For this sort of a polynomial, I know that I will have the desired poles. Yeah, so someone has told me where to place the observer poles, and from that I can cook up, because it is a monic polynomial, I can uniquely cook up the characteristic polynomial, the desired characteristic polynomial in closed loop, right? So therefore, this is it. So now you see it turns out it is tantamount to just equating coefficients on either side. So I will, because I have done the calculations here in details, no harm in showing you what the calculations are going to be. So what then it turns out to be is this determinant, and then you have S, let me see, then you have, hang on, so this is yeah, Si minus, so this is minus 1 minus, there is a minus sign missing here, no, so it is Si minus A minus LC, so this is a minus sign, correct, now it is right. So this is going to be S, this is going to be minus of L1 plus 1, going to be 0, 0, S minus L2, minus 1, minus 20, 11 minus L3, S plus 8, okay. So this is the determinant that I require to be equal to this 60, 1100, 6000, yeah, 60S squared plus 1100S plus 6000. So I need this, and my unknowns are L1, L2, L3. So that would mean, so if you do a little bit of calculation and simplification like I did, you would get this as plus 8 minus L2 times S squared plus 11 minus 8 L2 minus L3 times S minus 20 L1 plus 20, that must be equal to S cubed plus 60S squared plus 1100S plus 6000. Immediately you might see that, well, I can equate the coefficients, and in many of these coefficients there is only one term that is appearing. So it is almost as simple as evaluating in the controller canonical form, in the observer canonical form, though not exactly, but yeah, but you see this one term here, for instance this involves both L1, L2 and L3, right, both L2 and L3. So what I can do is I can basically evaluate L2 directly from here, L1 directly from here, and then plug in the value of L2 here and evaluate L3, yeah. It is a little bit more calculation, but not really very difficult, yeah. So if I want to give this a linear algebraic formulation, yeah, I can just write this down in a very straightforward way of the form Ax is equal to B type of simultaneous equations, yeah. If I want to be rather pompous and give it that sort of a look, yeah, I can write it in that fashion, but you know, here it is very easy to see what the solution is going to be. So here are my observer gains, you see L1 is going to be minus 301, L2 is going to be minus 52, and L3 is going to be minus 673, right. So these are going to allow me to design my observer gains independent of the controller gains. So now, having completed this story, let me draw the full diagram. So here it goes. So this is the plant, this is the full controller and observer put in place together. Let me try to be a little neat than my usual standards, yeah. So this is the plant, this is the Y that is coming in here, yeah, this is being subtracted from this is the Y hat that is coming out. So this is my observers integrator, yeah, and this is of course the vectored form coming in here. This is B. Oh wait, hang on. So I need a summer here so that I can feed back through the A here. So this is A, yeah, so this is my A. So then this is the B matrix, and this is where the U is coming in. This is of course the Y, which of course I can tap out like this. So this is my U, this is the integrator of the observer, right. So for the observer of course I am going to tap out of this observer here, but before that let me just draw the observer independently. This is the C matrix, this is the observers A matrix, yeah, and this of course gets added here like in the actual plant. So this is of course Y hat, right, and this Y minus Y hat is a scalar which gets multiplied with this L. So this L is something that I have evaluated here, minus 301, minus 52, minus 673. Check my calculations, yeah, I have the habit of making these mistakes here, minus 301, minus 52, minus 673, minus 52, minus 673. So it's of course a vector that's coming out of here. So this is L times Y minus Y hat, yeah, so this is coming in here, alright. So then this so this LC comes in here and it gets added. So let me not draw the arrow here because it's going to get added here. Oh, this is going to get added here, yeah. So this is going to get added here. So A x hat, so this is x hat of course, this is x dot, this is x hat dot, yeah, and of course you have B matrix here, yeah. So to the B matrix you of course add the same U that you have here for the actual plant. But what is this U? Yeah. So now this we are going to tap out of here. This is going to be the controller. This x hat is being taken out through here, and then we have this K, which is again something I obtained in the previous lecture. Let me take a look at the K parameters. Hang on. Yeah, minus 6020, minus 1081, minus 52. Yeah, minus 6020, minus 1081 and minus 52. Minus 6020, minus 1089 and minus 52. Yeah, so that is my K. Remember, this is my L and this is my K, independently designed. Alright. So then the states x hat being multiplied by this, they become a scalar now. Yeah, so this Kx, this gets added here, and this is the external reference signal R. Yeah. So this is the entire control scheme, right. So what I have designed is, I have designed this K block here and I have designed this L block here. The remaining parts, this B and C and all of this, you see, this I already know. This is tantamount to identifying the system, right. So if I model the system accurately, if I know the system's model well enough, then I will be able to capture that model in a software. So you see, in this whole scheme of things, the entire plant is just this, and I have not laid my hands on this. So this plant could be entirely inside a box which I have not touched. All that I have done is with what is available at the output terminal of the plant and what is available at the input terminal of the plant. Yeah, that is all that I have used. So instead of just passing this R, I have used this, I have extracted this output, passed it through this observer model. Yeah, so this is the combined observer controller that I have designed for the example that we have chosen. So with that we kind of come to a sort of a culmination for whatever we wanted to cover in this course. That by no means suggests that that's the end of it and that's all that we have discussed, we have to discuss for the undergraduate level. There are several other topics which we might have covered maybe in a course with a little bit of more time permitted, but nonetheless what we have done here we should feel kind of winds up the story in a nice fashion. So let's, in the time that's remaining now from now till the end of this lecture, let's quickly try to recapitulate whatever we have seen in this course. So right at the beginning we saw Laplace transforms, yeah, we devoted some time to seeing properties of Laplace transform, right, and then we saw that these Laplace transforms are particularly useful in solving constant coefficient ordinary differential equations, right, and then we saw that if you ignore the initial conditions, if you ignore the non-zero initial conditions, yeah, and you set them to 0, then what you obtain from this differential equation is a transfer function which gives you a description between the input signal and the output that is obtained, right. So that is basically the 0 state response that can be completely characterized by the transfer function of a system. Then we went into modeling, we saw electrical systems, we saw electromechanical systems, we saw mechanical systems, we saw electromechanical systems with like a motor with gears, yeah, we understood all of those systems, we saw how you can draw analogues from one to the other. We saw that for every mechanical system you can always have this electrical representation, right, but for every electrical circuit you may not always have mechanical representation because of the fact that the mass blocks are what prevent you from doing that. So we briefly touched upon this idea of so called inerter. Of course we did not go into any details, but we just introduced you and told you that there exist objects like inerters which can act as the electrical analogues of capacitors and inductors, right. So after delving briefly into these aspects of modeling, what we then went on to was a brief journey into the so called aspect of stability, right. So we first of course started off with, of course before that we actually covered the steady state behavior of systems, right, steady state behavior, and then we saw the damping of a typical second order system, we saw these performance metrics like rise time, peak time, settling time, percentage overshoot, yeah, we saw all of those, how they can be characterized for a second order system with respect to the locations of the poles, right. We saw the effect of additional zeros and poles to a second order system, right, and then we moved over to the types of errors that exist in a system, the error introduced due to a step signal, a ramp signal or a parabolic input, yeah, and we saw how the type of the system, that is the number of poles of the system at the origin, and they tell us these error constants, the Kp, Ka, Kv, right, for the different types of systems, right, and then we went into the question of stability because all of this error analysis only makes sense if your system is stable in the closed loop to start with. So the first tool that we saw for stability was this Routh-Hurwitz criteria, this Routh array. We tried to go a little deep into this Routh array and try to understand beyond what most textbooks cover as to what this Routh algorithm is all about and why it works. We stopped short of giving you a complete rigorous proof, but hopefully with whatever we have discussed you are now in a position to understand and appreciate why that table works the way it does, yeah, and how those special corner cases like when you have a row of zeros or when you have only the entries in the first column becoming 0, what they actually imply insofar as the original polynomial is concerned, right, and we saw that how it makes sense to take the derivative and continue with the next row when you encounter a row of all zeros and why that makes sense, right. So we actually tried to go a little deeper and understand those aspects, and hopefully with that we have a nice understanding of how Routh array works. So thereafter we went into this interesting topic called root locus, from which we saw that if you put a system in a closed loop configuration with a gain block, right, and if you keep changing the gain, then as you keep changing the gain from 0 to infinity, the root locus, that is the locus of all the closed loop poles of the system, they change from the closed loop poles, from the open loop poles to the open loop zeros, right. And we saw several different properties of this root locus. The chief property that you have to remember in order to derive any property of root locus is this principle of matching this angle criteria, right. If you match the angle criteria, you will be able to derive almost all of the properties of root locus that are outlined in a textbook in a pointwise form, right. That is at the heart of it. So we saw things like the importance of angle of arrival, angle of departure, right, the crossing of the imaginary axis, the fact that the root loci will be symmetric about the real axis, yeah, how many branches of the root loci will go to infinity and along what directions, right. We saw on which segments of the real axis can there be a root locus, yeah. Then we also talked about the complementary root locus, which is when the gain varies from 0 to minus infinity instead of plus infinity, and we saw how the rules of the usual root locus, they are tweaked again depending on just an application of this angle criteria, right. So we delved pretty deeper into that, and finally we wound that up, we concluded that discussion on root locus by seeing how you can design these well known controllers such as P, PI, PID, lag, lead, lag lead, all these different types of compensators. Basically it entails placing the poles and zeros of these compensators, and how by choosing their poles and zeros in a judicious manner we might get our system to behave in a desirable fashion. We might be able to place the closed loop poles at wherever we want them to be, right. But we saw that, well, at some level it was some sort of an art. In every system it was not always possible to get satisfactory performance, so the importance of simulation cannot be overstated in such a case, right. So we discussed all of that with root locus, right. So after root locus we delved into this idea of Bode plots, right, frequency response, where we saw the phase and the magnitude plots of the system, and from there we understood the meanings of certain terms like bandwidths, phase margins, gain margins, yeah, resonant frequency, yeah, many of these things we understood. Gain crossover frequency, phase crossover frequency, we saw them pretty distinctly and clearly. We also realized why certain systems are called non-minimum phase when they have right half plane zeros, yeah, that was very transparently apparent when we looked at the Bode plot of such systems, right. What was non-minimum about the phase in such a case, that is what we actually saw, right. Apart from that, it might be mentioned that of course Bode plot can independently allow you to design compensators, the same compensators that you designed using root locus technique, but of course because of lack of time and because we wanted to get into this interesting bit about state space methods, the modern control methods, we did not delve too deep into Bode plot based controller design techniques, although such techniques are very useful and you should see them used most often for CISO robust controller design, right. So we saw all of that, and then we went over to this interesting new paradigm, that was Nyquist criteria, where in the same plot you basically can see this the phase and magnitude reflected in the same plot, right. It was a conformal mapping that we saw, and just by counting the number of so called encirclements and keeping tab of that, we can actually say whether a closed loop system is going to be stable or not. Not just that, from the Nyquist plot we might also be able to evaluate the phase margin and gain margin independent of the Bode plot, right. So that is what we did with the Nyquist plot. Then we finally ended up with this M circle and N circle derivations for this polar plots, right. And with that we sort of brought to a culmination our discussions on classical control theory. It must be emphasized at this point that well, there are things like signal flow graphs which we have not delved into, yeah, which would probably form part of undergraduate controls course in many curricula, but of course we did not go into that. But if you are interested, you can go through signal flow graphs from standard textbooks. I am sure you will find that topic to be interesting as well. It essentially helps you in this block diagram reduction, something which we have touched upon in the context of error analysis, steady state error analysis. We have seen that it is helpful if you can reduce block diagrams, but SFG allows you to do that in a somewhat more elegant fashion, right. So SFG can be an interesting topic, okay. And then we went into this state space description of systems. So from an ODE or a transfer function, we saw how we can get to a state space form, that is x dot is equal to ax plus bu, y is equal to cx plus du, right. And then we saw these interesting different realizations. There are many other realizations that are of interest to us, but we saw chiefly three types of realizations. One was the observer canonical form, which we learnt later was its name. Initially when we introduced it we did not call it so, we did not give it any name for that matter. Then we saw the phase variable canonical form, and finally we also saw the diagonal or the Jordan form realization of a state space realization, yeah, of a state space of a transfer function, right, Jordan form realization of a transfer function, that also we saw, and we saw its state space description, right. And then having seen all of this, we went into these two important properties such as controllability and observability, and we saw how they were very closely tied to this property called minimality. In fact, joint controllability and observability is the same as minimality, right, and we have seen that whenever you have no pole 0 cancellation in a particular transfer function, it means that the system is going to be minimal, and that is also going to imply that the system is going to be controllable and observable both. And if a system is controllable and observable, which is what brought us to the last part of this course, then we saw that we will be able to design a controller to place the poles of the system anywhere we like, okay, right. That is a beauty of the whole thing. Now of course you might say anywhere you like, so maybe I want in a third order system, I want one pole to be complex and two poles to be real. Of course you cannot place that with real coefficients, right, because you have to respect those things, right. You cannot, I mean if you want a characteristic polynomial to have coefficients that are real, then you have to have, if you choose a pole at 1 plus 2j, then you have to have another pole at 1 minus 2j. So when I say that anywhere I like I want to place the poles, those are some restrictions, right, but that is very commonsensical. Yeah, so do not hold it against me and say that, well, you said I can place my poles anywhere you like, so I want one of my poles to be complex and two of my poles to be real. Can you design some controller gains? In theory I can design controller gains and observer gains, but the point is you will not be able to realize them because all you have to deal with are real variables, yeah, and using real variables you cannot realize complex quantities or complex numbers, right. So of course subject to that restriction as it stands, we can place the poles anywhere, but then I have also been quick to point out that there is still this problem of zero placement, right. So you have seen that although the zeros, their locations, we have seen this long back when discussing classical control theory, we have seen that the location of the zeros, although they do not determine the stability of the system, but they do have a bearing, yeah, on the weights of the different modes. So they do affect the response of the system, so they may not affect stability, they do affect the performance of the system, right. So in order to be able to fully dictate or meet any kind of performance metric, it is imperative that we have some tool at our disposal to be able to place these zeros. Unfortunately using LTI controllers this is only as far as we can get, right. We cannot design the controllers to place our zeros anywhere we like independently, at least as of now. So that is a restriction with which we will have to live, but then we should also appreciate that there is so much more we can do which would not have been possible if we had only concerned ourselves with the classical control toolkit, right, that is only root locus and Bode and Nyquist as our design tools. With those synthesis tools we could have only designed controllers that can only achieve so much, but with now the state space control method at our disposal, we are now able to design these systems in such a way that the poles can be arbitrarily placed anywhere on the complex plane, provided your realization is both controllable and observable, or in other words a minimal realization, right. So that is what we have seen. So hopefully we have sort of been able to paint a picture before you about what lies ahead, what the tasks that a control engineer is supposed to accomplish are, right. But with that, before we wind up, it is perhaps not fair that I just wind up this course giving you the impression that we have learned quite enough, right. There should always be this dissatisfaction lurking behind you that I do not quite know enough or maybe as much as I should, right. So in order to enhance or increase that discomfiture, let me just show you or indicate to you what more we could have done, not in this course, but what more is there for you to learn or pursue as you go into a higher, more sophisticated courses or graduate level courses of controls, right. So of course it is imperative that you have a background or a solid sort of prerequisite of linear algebra, right, you go through, because only then whatever we have now done with this Jordan canonical form, yeah, all of these have very beautiful representations in terms of elegant linear algebraic parlance, right, such as invariant subspaces and things like that, right. So for example you can take any system and you can split up the state vector into controllable and uncontrollable states, similarly observable and unobservable states, and then the most generic splitting up of the state vector can be like the controllable and observable states, the controllable but unobservable states, the uncontrollable but observable states, and the uncontrollable and unobservable states. So you can partition any state vector into these 4 parts, right, and subject to these you can see what the structure of the A matrix looks like, and all of that, yeah, you can intuitively kind of guess what this is going to look like, yeah, but if you want to understand this in a very sophisticated language, then you have to understand the tools that are at our disposal, courtesy linear algebra, right. So these are things, there is something called Kalman decomposition, right, that very beautifully reveals to us, and it will turn out that essentially it is these states that contain all the information that is required about the transfer function. So these will consist of the minimal realization, okay. So these are all the states that you need in order to cook up the transfer function, but nonetheless these other states, they are important for the internal description of such a system, right. So without, in their absence, you would be only grappling with a external description of the system. So there is this tool at our disposal. These will all be covered in a typical course on multivariable controls, right. Then in multivariable controls course you will also learn about what zeros are. You will see that even in a matrix, each of whose entries is a transfer function, right. So each of whose entries is probably a rational function, right. You can still end up with a situation where there are no zeros, where each of those individual entries have certain zeros, yeah, but the overall system, the MIMO system, the multi-input multi-output system, can have no zeros. So you need to be very careful about what the definition of a zero is in such a case, yeah. Then how do you realize a system in the multivariable case, right. What is a controller canonical form realization for the multi-input multi-output case? What is an observer canonical form realization in the multi-input multi-output case? What is a minimal realization going to look like, yeah. What can you do with the observability matrix, which is now going to be a wide or a fat matrix, a controllability matrix which is going to be a wide or a fat matrix, at best full row rank. What can you do with an observability matrix which is at best going to be a full column rank and a tall matrix, yeah. How can you cook up certain bases, or how can you cook up certain similarity transformations based on these rectangular matrices now, yeah, because now the observability and controllability clearly will not be invertible, right, because they are rectangular matrices, right. So there still exist things like pseudo inverses and stuff like that, left inverses and right inverses of matrices, which you will obviously learn about only in a course on linear algebra, right. So a course on linear algebra combined with a course on multivariable controls will give you a very good foothold over linear system theory in general, right. Then for example, if you want to go into linear time varying systems, which we have delved very slightly into, yeah, we have just scratched the surface, right. So there is something called a method of adjoints, which is used sometimes in very practical systems, right, yeah, method of adjoints. Sometimes this is used to simulate linear time varying systems, right. So such things you would want to learn, right. So in order to understand them, you will have to dig deeper into linear time varying systems. So such things could also be the content of some more advanced level graduate courses, right. Then here we are only dealing with systems of the form x dot is equal to ax plus bu, y is equal to cx plus du. So clearly this is a linear system. Now what if your system isn't linear? What if it's just non-linear function, right, maybe even state dependent, who knows. Excuse me. So what if this is what your system's description is, yeah, right. So this could be a non-linear system, right, for all I know. And how do you design controllers for this? First of all, how do you even analyze the system? So then you will have to be acquainted with things like Lyapunov theory of stability, right. This simple check of Hurwitz, whether the A matrix is Hurwitz or not, will not work there. This will only give you some so-called local stability results. So if you want to get to global results, global uniformly asymptotically stable, yeah, those kind of results, then you have to do a course on nonlinear systems. And while doing a course on nonlinear systems, you will be introduced to a lot of other interesting phenomena, such as you could have multiple equilibria of the system, right. and then you could also have phenomena such as chaos. You can also have a finite escape time. So in our case, in the linear systems, even if a system is unstable, it will only, your states can only go to infinity as time t tends to infinity, whereas a nonlinear system has no such restrictions. A nonlinear system, the state, in a nonlinear system, the states could potentially go to infinity even within some finite time, right. So those are some other interesting phenomena that begin to emerge. So first of all, what is the condition for the existence of a solution of a nonlinear system? Yeah, there is something called Lipschitz criteria, yeah, and then uniqueness and existence of the solutions of these differential equations. Those are in fact not beyond doubt in case of nonlinear systems. So your system has to have some nice properties, so to say, right. So multivariable controls, linear algebra, nonlinear controls, these are all graduate level courses that you can pursue, for which the starting point or the launch pad would be a course such as the one we have just covered here, right. Then there could be also optimal control. So for example, now someone is already telling you where to place the poles of the observer and the controller, but now suppose no one is directly telling you or specifying to you what the poles and what the pole locations ought to be. Instead, someone tells you that I want to spend at most this much energy, right. So this could be my maximum, so my actuator has certain limitations. I cannot have a control signal that goes beyond this value, or I cannot spend so much energy on the control signal, otherwise the system will get heated up and it will burn out, right. So I integrate the overall energy, or I integrate the power, yeah, over the entire time duration over which it is active, and I find that it has to be limited beyond to below a certain quantity, right. So then you get into cooking up these cost functions, yeah, optimal control based formulations of what the control law should be, and even then it turns out that for these linear systems you often end up with a linear state feedback. So this linear state feedback isn't as useless as it might have initially appeared to be. Already of course you have seen that it allows you to place poles, but this linear state feedback is also can also be an optimal control law in many cases, right, when your cost functions have certain natures. Then you end up eventually solving things like so called Riccati equations, right, to obtain what this gain matrix would be, what the gain matrix for the K matrix would be for such systems, right. So that will come within the purview of some advanced course such as optimal control, right. So these are all advanced level courses that you could launch into hereafter after going through this particular preliminary course on undergrad controls, right. Apart from that, there is also this idea of so called robust control, right. So you learned about this Routh-Hurwitz criteria, where you check whether a particular polynomial is stable or Hurwitz or not, right, whether all its roots are on the left half plane. Now there's something called Kharitonov's theorem, where you will have a polynomial a0 plus a1s plus dot 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 till an s to the n minus 1 plus s to the n, yeah, and all of these a0 can belong to some interval, yeah, in general ai belongs to some interval ai minus to ai plus. So this is basically a whole family of polynomials now, yeah. So this is then a whole family of polynomials, not just a single polynomial, and it turns out that by this striking result due to Kharitonov, you can just apply the Routh-Hurwitz criteria on exactly 4 polynomials irrespective of the degree of the polynomial. Even if it is a 2000th or 2 million degree polynomial, you need to just apply Routh criteria 4 times on 4 polynomials. If each of those 4 polynomials happen to be Hurwitz, then every polynomial in the value in the family, right, where a0 can choose any value between this, a1 can choose any value between this interval, and any ai can choose any value within this interval, yeah, you just need to perform the check 4 times. So in some sense you will get some idea about the robustness, yeah. So if you perturb these coefficients, even then will your system be Hurwitz, will your poles all remain on the left half plane, right. So that is one way of checking for parametric uncertainties, and in the face of parametric uncertainties whether your system still remains stable. So that is a robustness technique, so that comes within the purview of a course such as robust control. Then of course you can have, instead of using this simple state feedback like law, you have this plant here, right. What we then typically do is we also have some sort of an uncertainty here. This uncertainty could be structured or unstructured, right. So now you say that this whole plant is characterized not by this plant transfer function, the nominal transfer function alone, but by this perturbation, where this perturbation is somewhat bounded by some gamma, okay, some norm, the norm of this perturbation is somewhat bounded, that is all you know. And in the face of this, what you are required to do is you are required to design a controller. So when I say K, it is basically K of S, yeah, which will stabilize this entire plant, this uncertain plant, this family of plants, alright. So this is a fundamental problem of robust control, right. So of course we design all these controllers in the state space domain. When we deal with multi-input, multi-output systems, yeah, these all turn out to be problems formulated in the state space domain, and these problems eventually lead you to things called LMIs, that is linear matrix inequalities, yeah. So eventually all of this formulation of a robust controller, the quest for a robust controller ends with formulating certain LMIs and trying to solve for those LMIs, right. So that is again another interesting course which primarily focuses on how to synthesize controllers for a whole family of plants, not just for a particular plant, where the whole family of plants means it could be some parameters that are varying, and despite the variations of these parameters, your plant has to be stabilized by this controller, right. So that is what this entails. So these are all interesting, exciting courses that are there to look forward to, for which hopefully we have been able to generate enough curiosity in your minds through this undergrad controls course, and you understand these ideas well enough, and you will see that even though many of these ideas do not have ready extensions to the MIMO or multi-input, multi-output case, or to the nonlinear case for that matter, but a lot of these intuitions will help. For example, an understanding of this Nyquist criteria will actually help you in seeing how something like a describing function in nonlinear controls works, right. So when you talk about passivity, when you talk about circle criteria, yeah, the Luray type nonlinearities in nonlinear controls, you will see that again you will have to harken back to these ideas of Nyquist criteria. Even a classical control technique such as that helps provide you with multiple insights about the problem, right. So that is why, although in this course we haven't been able to get to very sophisticated topics, because of course we wanted to restrict ourselves to those things which do not require very involved or advanced linear algebra, yet hopefully if you have developed your concepts well enough on these topics that we have covered, you will see a lot of these things, a lot of these courses that come up hereafter will follow readily, yeah, and you will be able to follow many of the arguments or the logic that is presented, yeah, if not see also how some of these tools and techniques that we have developed here will also be extended quite easily, in fact, in many cases, right. So with that hope, I sincerely hope that you have managed to extract something out of this course, and that you have been interested in this course. I have been able to generate at least some semblance of interest in your minds about what lies ahead, not just what we have done so far, and if that has been the case, I would consider that this endeavor has been somewhat of a success. I wish you all the best in future for your lives, and hope that your journey for your foray into further and further sophisticated topics and control systems continues, and may this be just the beginning of many more great things to come hereafter. Thank you very much.